Okay, let's do an example. Okay, so let's say we have a solution, 50 milliliters of 0.030 potassium hydrogen phthalate. You'll see this abbreviated KHP. Are you doing a KHP titration? That might be next week, or in lab. You're doing a weak acid titration next week. I don't know what your acid is. KHP is often used to standardize sodium hydroxide to figure out the concentration of sodium hydroxide using a titration. Okay, so it's pretty common to see this acid. And that is not the formula, that's the abbreviation. Okay, that's an easy one to mix up. So we put that in a flask and we titrate with 0.0964 molar sodium hydroxide. The Ka for KHP is 3.9 times 10 to the minus 9. So again, the first thing I want to know, we are going to go through each of those points, figure out the pH at each of those points along the titration curve, but I want to know where we are in the curve in relation to the equivalence point. So the very first thing I'm going to do is calculate the volume at which the equivalence point occurs. So again, I typically do this personally as a dimensional analysis problem. 1 second. Okay. And so in doing that, I'm going to start with my volume and concentration of the weak acid, and we're going to figure out how many moles of base, how many liters of base we need to completely react. And keep in mind that we are doing this reaction. We're going to have HA plus OH minus forming A minus plus H2O. Okay, this reaction is going to occur to completion. Once we mix any amount of hydroxide with the weak acid, it reacts completely, right? The other thing to point out here is that these react stoichiometrically 1 to 1. Okay. All right, so I'm going to start out with my concentration of KHP. So 0.0393 moles of KHP per liter of KHP. We're going to multiply by the volume, 0.05 liters. We have 50 milliliters of that. KHP, it wasn't stated in this problem, but this is a monoprotic weak acid. All right. So for every 1 KHP, it's going to react with 1 hydroxide, but I guess you can get that from this equation. So for every 1 KHP, I guess we should also do this. We get 1 mole of H plus. Okay. One mole of OH minus is going to react with 1 mole of H plus. And then we can, because we have moles of hydroxide at this point, liters cancel, moles cancel, we can use our concentration of the hydroxide to find out the volume that's required. So we have a concentration of 0.0964 moles OH minus per liter. Okay. Multiply all of that out, and I'm going to convert to milliliters. I get 20.4 milliliters. Thoughts on dimensional analysis? That thumbs up? Okay. Head shake. That's fair. So one of the things that I've noticed in the past is that people will often solve these problems in a way that I wouldn't do. But it's logical, I think, somewhat. And I'm going to show you a way to do this, especially if you Google how to solve this problem. You're going to end up possibly with something like this. Now, this is not a dilution problem. Okay? But some people will try to solve this with the dilution equation. And you'll see this on the internet. It's technically not correct. But what this equation is saying, if you have moles per liter times liters, that's moles, right? Moles equals moles. And what we're saying at the equivalence point is that moles of HA equals moles of OH minus. So it kind of makes sense. If everything is 1 to 1, you can get away with using this equation. But I don't want you to use this equation. If you want to use something like this, I'm going to give you a slightly better equation, okay? So here's what we go. So we're going to do moles of H plus times the molarity of the acid times the volume of the acid equals moles of OH minus times the molarity of the base times the volume of the base. And this will work. So let's look at solving this same problem using this equation. Let's all do it sort of individually at first, and then we'll meet up. I haven't worked this one out necessarily. We should get the same answer though, okay? The units make no sense, but that's okay. We're going to keep going. You'll use it anyways, I know it. Oh, it's a secret. Okay, yep. Secret meters. In this equation, we're solving for the volume of the base, right? We want to know how much base needs to be added. Okay. So that's what I come up with, that bottom line there. And I believe it should come out to 20.4. I can double check. Yeah. Okay. What do you think? Yeah, there's a question.
Not what you did just now, but what you did before.
Yeah.
It's like the same exact thing that we did for weak or for strong acids and strong bases.
Exactly.
Is there any time that's going to change, or are we using?
No.
It's just going to be the same for weak acid or strong acid.
It is going to be the same. And the reason is that the reaction that's taking place is reacts to completion, acid plus base forms water plus whatever else. Good question. What do you think of this formula? Is that more logical to y'all? You can choose which way you want. Now here's why I want you to use this equation and not this one. Okay? Let's say we're doing the same problem. We have 50 milliliters of the 0.0393 molar KHP, and now we're going to titrate with same concentration, 0.0964 molar calcium hydroxide. Now solve the problem. What's that? You plug in the 2. Yeah. So here we're going to have 2 moles, sorry, wrong side. Got excited. 1 mole still of the acid. That's 1 H plus for every KHP. That's where that's coming from. Same concentration, same volume as before. Now for every 1 calcium hydroxide, we have 2 moles of OH minus. So that's where that's going in, okay? same concentration. And we're again solving for the volume of the base. Okay. So what we tend to see is that if people are using this M1V1 style equation, if you don't recall using the moles, or you don't account for the fact that for every one, for instance, calcium hydroxide, you get 2 hydroxides, then you make a mistake, and it's an easy mistake to make. And so if you use the equation with the moles times M1 and V1, whatever, then you should be fine. Thoughts on that? Or maybe that makes more sense than the dimensional analysis. I don't know. I like dimensional analysis, but yeah. Questions? Okay.
Can't you reduce equation to the other one though?
This to this? What do you mean? Yeah, if it's 1-to-1, that's fine. This will also work too.
No, I mean the dimensional analysis.
Oh, it does end up being the same. Yeah. I don't understand why that we don't include this equation in the textbook, this moles one. Because I do think it is a bit more logical. You're literally saying moles equals moles, right? And that's what we're saying at the equivalence point, moles equals moles. Anyway, that's a little bit of a digression. I think there must be a mistake somewhere. Yes, I don't know which one is the right one. What do I keep using for the? Let's see. Ka of KHP. Take a break while I do this. Yeah, times 10 to the minus 6. Okay, thank you. Let's keep going. Okay, so let's start calculating the pH before any base has been added. So now we have our KHP. Again, it's a monoprotic weak acid. We'll just call it HA, so we don't have to write out the whole formula, which is long and it's a lot. Okay. So again, this is a weak acid problem. We're going to take our weak acid. We haven't added any hydroxide, right, before any base is added. So all we need to worry about is the equilibrium. Okay. Hopefully this is a relatively easy problem at this point. We start with our initial concentration, subtract x, add x to both sides of the products. At equilibrium, we're going to end up with 0.0393 minus x moles per liter of HA, x moles per liter of A minus, and x moles per liter of H3O plus. We set that equal to the Ka, which is 3.9 times 10 to the minus 6, x squared over 0.0393 minus x. In this case, x is going to be small compared to the 0.0393. So we can ignore that, make our lives easier. We'll end up with x equals 3.91 times 10 to the minus 4 molar, which is the H3O plus concentration, right? So we can do minus the log. of 3.91 times 10 to the minus 4. And we'll end up with 3.41. Acidic, good, that's promising. Everyone okay with this problem? Okay. Questions on that? Let me give you a chance. Questions? Yeah.
Wasn't the KA 3.9 not
Yeah, you know what? That caught me too. It might be the 3. It might be the 6. It would make more sense to be the 6. Okay. All right, so now let's add some base. What is the pH when 10 milliliters of sodium hydroxide has been added? What was the pH of the equivalence point? Or excuse me, the volume of the equivalence point? 20.4. And so we know that we are, before the equivalence point, we're only adding 10 milliliters. We aren't at 10.2, so we can't really just say pH equals pKa. I'm sorry. We'll get there. So let's solve the problem. So we know that we have to react some of the base with the weak acid, or all of the base with the weak acid. So we have to do a reaction table or a BCA table. Okay? From that, we're going to get moles of HA left over, moles of A minus that have been produced in the reaction, and from there we can use the Henderson-Hasselbalch equation. Okay? So, all right. So we're going to have our HA plus OH minus forms H2O plus A minus. Again, we're going to do BCA, right? So we need moles. So I'm just going to write this here. So 50 milliliters of 0.0393 molar gives us 0.001965 moles. Okay, now I'm going to put that in BCA. Ten milliliters of 0.0964 molar. It's going to give us 0.000964 moles of OH minus. Okay. So we can subtract 0.000964 from the reactants and add it to the A minus product. And we're going to be left with 0.001001 moles of HA. Then we need Henderson-Hasselbalch equation. pH equals pKa plus log of A minus or base over HA or acid. Y'all have very active devices today. You know, it's probably because, you know, this is super exciting and you just want to record it, but yeah.
How do we know that we should use the
Henderson-Hasselbalch? How do you know we should use Henderson-Hasselbalch? Great question. When do we use Henderson-Hasselbalch? Only? Buffers. Only for a buffer. And how do we know that this is a buffer? It has both the weak acid HA and the conjugate base A minus. that work for you? Okay. Yeah, so anywhere along that titration curve, after we've added some hydroxide, but before the equivalence point, that's a buffer problem. Okay, so if you're picturing this titration curve, that whole region, region 2, is a buffer problem. Okay. All right. Excuse me. Do you want me to find total volume and we put concentration in here like we're supposed to, or are we just going to use moles? Moles. Everyone understands that we're supposed to use concentration. But why do we have to not use the volume? Yeah, we're dividing by the same number. Okay, good. Then I will definitely go ahead and do that. All right, so pH equals minus the log of 3.9 times 10 to the minus 6 plus the log of A minus. We're going to say that is the 0.000964 moles A minus, and then the 0.001001 moles of HA. If you wanted to use the volume, you've got to keep track of how much we've added. We've started with 50, and we added 10, so we have a total of 60 milliliters. So keep an eye on that, right? If you want to use the volume, you've got to add up those volumes. Okay, so the pKa is 5.41, and I didn't calculate this out, and I don't feel like it, so do that. pH equals 5.39 at this point in the titration curve. Does that make sense? Question? How do you know when to use the ice table or when to use the BCA table? Great question. So we are going to use a BCA table. I like to call them reaction tables because it makes me think, oh, we have to have a reaction, not an equilibrium. And ice is for equilibrium. Okay? So we have to have HA plus OH minus. We're all losing, I like it. Happy middle of the semester, this is great, yeah. We need like a show down here instead of, is that a marching band here now? You do a xylophone or anything? No? Is that what it's called? Yeah. Okay. What do you play? Trumpet? Are you performing tomorrow? Nice. Good luck. Anyone else in the band while I'm off topic? All right, what were we saying? Oh, I didn't answer your question yet. We have to have a reaction. So the HA is reacting with OH minus, so that's when you use BCA. If there's no reaction that's going to completion, you have your equilibrium arrows. That's ice table. And essentially in this problem, our Henderson-Hasselbalch is taking the place of the ice table, right? Okay. Cool, okay, so pH has increased, that's good, yeah. We have disappointed, what's your name? Because we keep talking, what's your name? Yeah. Naomi, we've disappointed you because we weren't halfway to the equivalent, right? So that's another thing to keep in mind, right? We ended up subtracting a small value from the pKa, okay? If we were all the way to halfway to the equivalence point, okay, we would have had to have added for this problem 10.2 milliliters of base, and we would know that the pH equals the pKa, which would be 5.41. All right? We're just shy of that, and so the pH should be less than that value, right? And we're just slightly less of that. So that's good, that's another check you can do on if your math is working out correctly. If we go past that halfway to the equivalence point volume, pH should be greater than pKa. Okay? All right, questions on that? Okay, let's do the next part. pH at the equivalence point. Okay. So we have completely reacted our weak acid plus the hydroxide, right? That's the definition. At the equivalence point, we have 0 moles of HA left over, 0 moles of OH minus, okay? And some number of moles of A minus. How do we figure that out? We could use a BCA table, a reaction table, right? But what else do we know? We can make it a slightly faster. Slightly less writing. Don't be so confused. I'm so sorry. The number of moles we start out with of HA is at the equivalence point going to be the number of moles of A minus. Okay? We've completely reacted the number of moles of HA with the same number of moles of OH minus. The only thing we've made is A minus. So those have to be 1-to-1, completely transferred. So if we know the moles of HA at the start, these completely react to form A minus. And so at the equivalence point, that is the number of moles that we started with is equal to, or that is the number of moles that we have of A minus. What am I doing? Okay, so whatever we start with in terms of HA, we end up with in terms of A minus at the equivalence point. That was written out terribly, I apologize. Okay, so we started with 0.0393 molar times the 50 milliliters, and we have 0.001965 moles of A minus at the equivalence point. If you want to do a reaction table, by all means, like, you'll get the right answer. It's just a lot more steps. Okay. But we have A minus in solution, right? We can't just get a pH from knowing that concentration. We need to do an ice table here. And in this case, we have an A minus plus H2O in equilibrium with HA plus OH minus, excuse me. So we've got our equilibrium arrows, so we need to do an ice table. We have to use concentration in our ice table, right? So this is an important step not to forget. So we need concentration of A minus. We'll take our moles, divide by the total volume. What's our total volume? Okay, we started with the 50 milliliters. We're at the equivalence point. We had to add 20.4 milliliters of base to get there, right? We only know that from having done that problem before. Okay. And so we have a total volume of 70.4 milliliters, or 0.0704 liters. Okay. that's going in there. That gives us a concentration of 0.0297 moles per liter. Nope, 279, excuse me. Okay. And now we can use that in the ice table. This is just a weak-based problem. We have one other thing we have to calculate though. What is it? There's one other thing that isn't given in the problem. For a weak base problem. KB. Yep. Okay. So we need our KB. And if you recall, KW equals KA times KB. So we're going to take our KW, assume 25 Celsius. So we're 1 times 10 to the minus 14 for our KW, divided by the KA, which is 3.9 times 10 to the minus 6. And that is not in my notes. 2.56 times 10 to the minus 9. Cool, thank you. Okay. And we need to set up our equilibrium. Okay, so we had 0.0279 moles per liter. I still like writing this part out, at least for the ice table. So we're going to have x squared divided by 0.0279 minus x. X is definitely small compared to the 0.0279 because our KB is very tiny. So that goes away. Multiply that out. We're going to get x equals 8.46 times 10 to the minus 6, which is equal to the hydroxide concentration. Remember, we have this part of the weak base problems. You find x, that's hydroxide concentration. So we can find POH and then pH from there. Okay. So all of the things that we've done in the last couple weeks here, these are all coming together for titrations. Minus the log 6 times 10 to the minus 6. And I get 8.93. Okay. Does the pH make sense? It's basic. We know at the equivalence point for a weak acid titrated with a strong base, the pH must be a base, basic. So that's reasonable. Okay. Questions on that problem? One more, 10 milliliters past the equivalence point. This problem works just the way same problem did when we did the strong acid titrated with the strong base. So we can go through, set up a BCA table, figure out moles of hydroxide left over, or, and I kind of prefer this way personally, but it's up to you. You can know that we are 10 mils past the equivalence point. We can figure out the number of moles of hydroxide in the 10 milliliters, and then find concentration from there, and then do minus the log of the concentration of hydroxide. So I'm going to do that method, and then we can talk about others if we want. So, okay. So the number of moles of hydroxide, there's an excess. So we're going to have our concentration 0.0964 moles per liter times 10 milliliters, because we know we are 10 mils past the equivalence point. So none of this has reacted. So we get point, do I have too many zeros? No. 0.0, maybe. .000964. Yeah, that makes more sense. Okay. Well, that's moles of hydroxide in excess. We want concentration because eventually we want to find pOH. All right. So we need a total volume. We started with our 50 milliliters of the KHP. And to get to the equivalence point, we had to add 20.4 milliliters. And now we are 10 milliliters past that. So the total volume should be 80.04 liters, excuse me, milliliters. So we get a concentration of 0.0120 moles per liter. Plug that into our pOH. We get 1.92. And so the pH equals 14 minus 1.92, or 12.08. Very basic. That's great. We have excess hydroxide. Make sense? Questions? Okay. Real quick here, because I kind of want to finish up this section. Titration of a weak base with a strong acid. Okay. Take a look at the titration curve. It's here in comparison to that of a strong base titrated with a strong acid. For our weak base, again, we start out at a basic pH. We form a buffer, so this whole region here is a buffer region. We get to the equivalence point. You'll notice that the pH at the equivalence point is acidic. And then eventually in excess, we're dependent on the amount of excess H+. Okay. Why is the pH -7 at the equivalence point? We know we're going to react our base, B, with H3O plus or H plus, however you want to write that, to form BH plus and H2O. But this is a weak acid, and it's going to have an equilibrium with water. So we're going to form B plus H3O plus. Okay, and it's this equilibrium that is the dominant equilibrium at the equivalence point. You'll notice there's H3O plus present as a product, and that is why the pH is acidic. Okay? Make sense? All right, I have a couple problems. Should we do them or no? Amazing. Have a great weekend, everyone.